Let's start with some warm-up questions on naming. We have this molecule right here. How do we even begin? I like to take a puzzle piece approach when it comes to nomenclature, and that is finding the parent chain. So we want the first name, tell me how many carbons in the parent. That will be my parent right there. It's a cyclohexane, 6 carbons gives me a first name of hex. Only single bonds in the parent chain gives me a last name of ane. And then I look at substituents and functional groups. I have a methyl group. Well, first I should number it so I know which way I'm going. I'm looking for 2 things when I'm numbering. One, the total lowest set of substituents, the total lowest set of numbers. And so I'm not, for example, going to start here and go around that way, because if I go this way, 1, 2, 3, 1 and 3 is the total lowest combination that I can get. 4, 5, 6. This gives me, on carbon 3, I have a methyl group. And on carbon 1, I have a ketone, which gives me the last name O. In a situation like this, the ketone is the highest priority on the ring, self-implied to be number 1. So you don't have to specify the number. And then you just put the puzzle together, which is 3-methyl for the substituent, 3 dash because it's letter to number to letter. And then we have hexane, well, cyclohexane, because it's a ring. Let's not forget that right there. Cyclohexane. But because we have the functional group starting with a vowel, we drop that E and put O-N-E, giving me 3-methyl cyclohexanone. Pretty simple, hopefully, pretty straightforward, a good warm-up question. Let's crank it up just a bit with a molecule that looks like this. What do you think? Easy, medium, or hard? There we go. Hello, Coachy. I don't know if I said that right, but it is good to see you. First thing we'll do is identify the parent chain. That will be this chain right here. We'll number it from the side that A gives me the total lowest set of numbers, but also in the case of an aldehyde, that has to be number 1 when it's the highest priority. So that will be 1, 2, 3, 4, 5, 6. 6 carbons in the parent chain gives me hex. Only single, you know what, let's mix it up a little. Let's go with, can't even put a pi bond anywhere. I guess we'll do that. We'll put a pi bond in there. There we go. Now we have an ene, and that'll be 4 ene for the parent. Then we'll look at all the substituents. On carbon 3, I have 2 methyl groups. I have to include a number 3 for each of the methyls, so 3, 3, and then I still have to put dimethyl to show that it's 2 methyls. The other substituent I have is an alcohol on carbon 5. Because I have an aldehyde, the alcohol is not the highest priority, so it becomes a prefix of hydroxy, 5-hydroxy. Then I have an ethyl on carbon 1, 2, 3, 4. I did not give this thing too many bonds. Okay, just making sure. I made up the problem on the spot, so I didn't want to put too many bonds in there. So we have 4 ethyl. And then finally, for the functional group, we have an aldehyde on carbon 1. That would be 1-al, but again, the 1 is implied. It's self-understood, so we don't need the number there. Nagy, all the way from Ireland, welcome. Imran has an answer for us, so let's see if that works out. We start with all the substituents. That's an M for methyl, H for hydroxy, E for ethyl, E, FGH, IJKLM, so we're going to go ethyl hydroxy dimethyl. So that is 4 ethyl, 5-hydroxy, 3, 3 dimethyl. Then we go to the parent. You can drag that 4 out or leave it where it is. I'm going to call it 4-hexene. Drop that E because al is a vowel. So that actually comes off. And then al for the aldehyde. for ethyl 5-hydroxy 3,3-dimethyl 4-hexenal. Don't forget the ene. And bonus question to you, what is wrong with this molecule? What happens if I allow this molecule to just sit in some kind of solution that has either acid or base? Let's get a copy of the molecule because this is very, very important and a good way to segue into the aldehyde ketone reactions. I have a group on this molecule that is not very stable as is. And that group, let me know in the comments if you know what it is. That group is what is going on this carbon right here. I have both an alkene plus an alcohol that is an enol. The enol will undergo what is called KET, keto-enol tautomerization. And that will give me a molecule that looks pretty much the same, except that the pi bond moved. So instead of a pi bond on the carbons and a hydrogen on the oxygen, the pi bond is now between the carbon and oxygen. We get that extra hydrogen here, and now I get a ketone. Keto-enol tautomerization will happen automatically when you have an enol and the keto form is more stable, because that keto form has a carbon to oxygen double bond, which is more stable than the carbon to carbon double bond. And the solution will automatically tautomerize, meaning it'll automatically do the reaction to give you the ketone or the aldehyde. Let's jump on over to a quick review from Organic Chemistry 1. One way that you can make a ketone or an aldehyde is by cleaving a carbon to carbon double bond. What reagent would I need to turn this molecule into not just a ketone or an aldehyde, but actually more than one ketone or aldehyde? What reaction am I looking at? And for the students who just joined, welcome, welcome. We are working on practice for aldehyde and ketone reactions. Don't worry about copying anything that I have on the screen. Just put live notes in the comments and I'll give you a link to the live session notes. The problems that we're doing are very similar to what I have on the aldehyde and ketone worksheet, not available on my website. All you have to do is put worksheet in the comments and I'll send you that as well. And yes, even if you're watching the recording, just leave a comment after the fact and I'll make sure you get those links. The reaction we're looking at is ozonolysis. If I react this with O3 as step 1 and step 2 DMS, I will get oxidative cleavage where the bond is cut, not just the pi bond, but also the sigma bond. And the shortcut for that, let's make it bigger so you can see. The shortcut is simply draw a line right there and add your oxygens in. Draw a line right there and add your oxygens in. That is where the carbon-to-carbon bonds will cleave. That is where we form the aldehyde and ketone. How do you know if it's an aldehyde or ketone? You don't have to worry about that, because if the molecule looks like it's an aldehyde, it's an aldehyde. If it looks like it's a ketone, then it's a ketone, meaning if I have a hydrogen here, it's going to be an aldehyde. It looks like these would all be aldehydes, so let's make it a little trickier. Let's add a methyl group right there. Now we have at least one ketone. The best way I find to figure out the product is not to try to guess what is going on. It's simply to number it. What do I have here? A long chain, 1, 2, 3, 4, 5. And then we can go in 2 different directions. I can go 6, 7, and then we'll call this A as a substituent, or we can call this 8, however you want, but know that it's 7 in a row. And then the 8th one sticks out from carbon number 5. 2 ways that you can do this. Some professors and some students like to just draw it exactly as they see it. 1, 2, 3, 4, 5, 6, 7. Number it so you know where to put all your pieces. And then what do we have on here? On carbon number 2, I have a carbonyl. Look at that. It's a ketone. On carbon number 7, I have a carbonyl. Because it's terminal, it automatically is an aldehyde. On carbon 5, I have a substituent with another carbon coming out of it that we called 8. And that also has a carbonyl, which is also an aldehyde. But we get a second product for this over here because we cleave this piece completely off. And that is 2 carbons with a carbonyl that happens to also be an aldehyde. Let's try one more. What is one way that I can get any alkyne whatsoever? So sometimes your professor will tell you the name of the molecule. They're not going to tell you the specifics. And I want that alkyne to turn into something that looks like this with an aldehyde. How can I make this from an alkyne? If that's what you see on your exam, what you do is very simple. Reverse engineer and say wherever I have that alkyne, wherever I have the carbonyl, that had to come from an alkyne. The fact that it's terminal tells me it was a hydroboration reaction because that's an anti-Markovnikov addition. And as soon as you notice it's a terminal aldehyde, then you put your reagents. We'll use B2H6, NaOH, and H2O2. You could have also used another version of boron like BH3, not as common for alkynes. 9-BBN is another pretty common one. And then to figure out what the starting molecule was, all you have to do is number it. It's a 5-carbon chain, and the pi bond is between the carbonyl carbon and whatever is next to it. So in this case, it's between carbons 1 and 2. So I'm going to redraw it with carbons 1 and 2 as an alkyne. Coming out of that, I have carbon 3, and then out of that, I have 4 and 5. Let's not forget the methyl group on carbon 3. And this is my starting alkyne that gave me the given aldehyde. That gave me the given carbonyl there, which happens to be an aldehyde. Right. If you're with me so far, let me see thumbs up in the comments. Let me know if you want to jump into something a little bit more intense, a little bit more difficult, or keep doing warm-up questions. Question: if it wasn't terminal, could it be oxymercuration? Yes, exactly why we check for that. Because if I gave you a similar reaction, so let's do the same situation. We have an alkyne, and somehow, some way, you have to turn it into a molecule that looks like this. Let's go with that one. This right here could have actually been one of two things. We identified the carbonyl carbon. That right there was an sp carbon from the triple bond. But the question is, was it a triple bond like this? Or was it, I'm going to do that in a different color. Or was it a triple bond like this? Now the answer is actually both. It could have been both, but here's what you have to consider. If I start with a pi bond, the triple bond where I have the green dots, then I have no ambiguity. I only have one reaction, where this would be 1, 2, 3, 4, 5, 6. 6 carbons, that is 1 and 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And then in this case, I would have to react it with oxymercuration, so HgSO4 and H2SO4, and it would go right here. But if I use the other direction as the starting molecule and put the triple bond between 2 and 3, then I potentially introduce 2 different products. And if your professor says no side products, your professor is saying, give me the one, not the other. So let me show you what I mean. If I have a molecule with the light blue triple bond between carbons 2 and 3, I still have carbon 1 over here. This is 2, this is 3, 4, 5, and 6. But now I can use either reagent. It doesn't matter because it's internal, so they'll both give me the same thing. I can do Hg ... or I can do B2 ... but I can get a carbonyl here or a carbonyl here, and that means I'm going to get 2 products, which your professor may not want, but I want you to be aware of it. So, Elena, I think it was your question. Very good question. Let me know if this both answered your question and showed you what could happen if we do have ambiguity. just for you, Leslie, just for you. We're going to turn my warm-up question into a synthesis question. I want to go from here to the aldehyde version. What would it take to turn that molecule into an aldehyde like this? You can use any reactions, anything that you can think of. What specifically is your first step? Because you don't want to jump right to the answer. You want to kind of break it down step by step and figure out where you're going to go with it. The first thing I like to do, as I teach in the synthesis session, if you haven't seen that yet, make sure you watch it, is to ask the two questions that will guide me in where to go with the synthesis. Question one, how are these two the same? And then question two, what is the difference between them? So first, we want to see what has not changed, so I know where to go with the reaction. And what hasn't changed is that I have these 7 carbons. And so I know that I keep my 7 carbons. What's different is that my bromine turned into an aldehyde, and I have to figure out how to do that conversion. How do I turn a bromine into an aldehyde? I don't know. I don't know of any reaction that goes like that. When I'm not sure what to do, I try not to think about the first step, and instead I look at the product and I ask myself, if I didn't have to contend with the starting molecule, if I didn't have to start with a bromine, is there any other molecule that I can use? Is there any reaction that I know to create an aldehyde from something else? I just did a sound test on my mic. Did you hear me coughing? Because I don't know how to mute on this thing. But yes, you did hear me coughing. Okay, well, in that case, I apologize for coughing in your ears. I guess that didn't work. I'll have to try something else next time. What reaction do I know that can give me the aldehyde? Well, I know I can turn it into an aldehyde from an alcohol. So if I take the skeleton and I take an alcohol at the terminal position, I should have done something trickier, but we'll keep that for now. If I take that alcohol, I now ask myself a different question. Forget this to the product. Do I know how to go from a bromine to an alcohol? Is there a single reaction that with one step will get me there? Esther says yes, and that is correct. One reaction, an SN2 reaction specifically, that will replace the bromine and give me the alcohol. And that's it. Now we have all the steps. Let's go and fill in the reagents. For an SN2 reaction, we look at what is on the molecule, make that the nucleophile. OH needs a counter ion, so we'll use NaOH. To make sure we get SN2 and not E2, we're going to put it in an aprotic solvent like DMSO. Then from the alcohol to the aldehyde, we'll use PCC. I see question with AlCl3. So AlCl3 is a very good Lewis acid catalyst, and that is going to help with adding something to a ring. So if this was a benzene ring and I wanted to add a group onto it, the AlCl3 is something that I would consider. So I like that you're thinking in terms of adding to the ring, but in this case, it wouldn't work. And the reason I would use PCC is that it's a mild oxidizing reagent. It won't turn it all the way into a carboxylic acid, which most of the oxidizing reagents will, except for this one, which stops at the aldehyde. The figure was small, so I thought the bromine is directly attached to the ring. I know some students are watching this on a mobile, so maybe I will try to do the next one a little bit bigger. But let's try something. Trying to think if I should go evil. What do you think? Easy, medium, or hard for the next one as I think about what to do with this molecule. I'm making these problems up as I go. Somehow, some way, we want to turn the molecule on the left into the molecule on the right. And how am I going to do that? I don't know where I'm going to start. So I'm going to ask myself the two questions. Question number 1, what is the same? And question number 2, what is different? What is the same is the fact that I have 4 carbons in my chain. That hasn't changed. I have 4 carbons. What is different, though, is what I have on the molecule and where I have it on the molecule. I have a bromine. C1 has a bromine, and that somehow goes to C2 with a carbonyl. So how do I turn a bromine on carbon 1 into a carbonyl on carbon 2? I'm not only swapping the group, but actually changing the position of it. Hello. I'm not sure how to do that. And by not sure, I mean there is no direct reaction. So I'm not going to worry about the starting molecule for a moment. And instead, I'm going to ask myself, if I have a carbonyl, what reaction do I know that can get me that carbonyl? And there are actually two ways that I can approach this. If I want to go the route with an alkyne, then I can say this came from ketone autotaumerization of an alkyne right there. Or I can go with the route of an alcohol and I'm moving the functional group. So these are two different reactions that you learn in Orga 1. Let's do both of them. Vincent, thank you. I appreciate that. Let's do both of them because in this chapter, you will have to show how to do some of your basics. You'll have a long reaction with a good chunk of it Orga 1. So one step back, if I have a carbonyl, that could have come from the hydration of an alkyne, and that alkyne could have looked like this, where the triple bond in question is right there. I turn that triple bond into an enol, and it automatically undergoes ketone autotaumerization, but I'll show you the enol right there. That would have been the pi bond with the alcohol. Not isolated, that's where it came from. And then the question is, how do I make that alkyne? In the interest of this is not an Orga 1 session, I'm going to show you very quickly because it is quite a few steps. To make an alkyne, I still don't know how to get there from one bromine because I know how to make an alkyne from a double elimination with a dihalide. That dihalide can have bromine or chlorine. It doesn't matter. So we'll use two bromines, one here and one here, a double elimination. So the question then is, from this starting molecule, if I already have the one bromine, how do I get the second one on there? And the answer is tricky. It's that we don't, because you can't, or not a reaction that I know of. Instead, I look at this and say, oh, this was just the halogenation of an alkene. One step back, this was an alkene with a pi bond sitting right over here. And now I can turn that into a pi bond, that into a dihalide, and we're good to go. All we have to do is fill in the reagents. Question, why can't we use, I don't know what that reaction is, and therefore I can't use it. I don't know what it is, so I don't know if it works. To go from the bromine to the pi bond, we want an elimination, an E2 reaction. Any strong base will do. So for example, NaOH in H2O and heat. That right there is E2. Next, we will do a dihalide halogenation. We'll use Br2 and something inert like CCl4. This is an alkene reaction. I'm putting the chapters here because you cannot afford to forget your Orga 1 basics. And so this tells you what to review if you're not comfortable with it. Once I have my dihalide, I do a double elimination with NaNH2 and NH3 liquid. This is step 1. Step 2, I have to add H3O plus because it will deprotonate the terminal alkyne, which I don't want. H3O plus is going to add that proton back in. That's the alkyne chapter. The next step is to get the enol and ultimately keto enol autotaumerization. So I'll put KET over there. But to get the enol, we are going to use, this is a ketone, not an aldehyde, so we'll use HG. I don't know why I put that in parentheses. It's HgSO4 and H2SO4. I think I did that earlier too, because I'm used to the HgSO4. There we go. Yeah, I did the same thing. In an alkene, it's HgOAC2, so you need the parentheses for the 2, but here you don't. All right, and there we go. Those are all the reagents. Looks like pretending to be an Orga 2 reaction, and it was pretty much all Orga 1. The reaction involves hydration of an alkyne using the, oh yes, so that's the reaction right here. So this is oxymercuration. The other option that we can do is, let me just copy this over once more. because when you know multiple reactions, the good news is if you forget one, but you can think of another, you are still good to go and you'll still get full credit unless you're specifically asked for another reaction. The question we ask when we're not sure how to go from the reactant to the product is, if I don't look at the reactant, do I know of a molecule that will give me this as the product? The alkyne was my answer last time. Now I can think of another way. What if that ketone came from an alcohol? Now we have a new synthesis pathway where we ask, can I turn this into an alcohol? Now I do know how to turn a bromine leaving group into an alcohol, but the problem is they're not on the same carbon. So we'll have to use a synthesis pattern that I teach in the synthesis session, and that is moving the reactivity. I need to move the functional group from where the bromine is on carbon 1 towards carbon 2. And the way to do that is with a series of addition and elimination. In this case, because I have a substituent on 1, I will eliminate first to get a pi bond right there. And then I will add any halogen back, but I'll make sure to add it at this. Well, actually, why am I adding a halogen? I was going to add an extra step. Let's go right to the alcohol. This is easier than I thought because that's it. We're done. The alkene can give me the alcohol. All I have to do now is fill in the reagents. The first step is an elimination, just like we saw before. Let's change it up. Let's use NaOET in ETOH and heat. Any strong base will do. This is an E2 reaction. Then we go from the alkene to the alcohol. It's at the more substituted Markovnikov position, so we can use acid catalyzed hydration using simply H2SO4 in H2O. We could have also used oxymercuration for the alkene. It'll give us an alcohol. The alkyne, it gives us an enol. So this right here is an alkene addition reaction. Then once we have that alcohol, we simply oxidize it. Any oxidizing reagent will do, even PCC, because we're only looking for one level of oxidation. And there is another route to the product. First, dehydrohalogenation, right here, followed by hydration right here. Absolutely correct. That is perfect. Beautiful. If you're still with me, let me see some fire emojis in the comments, especially for, I think it was Leslie who wanted me to turn my let's do some oxidation questions into a full-on synthesis. And then let me know if you want to go back to kind of easy or just keep hammering the multi-steps, less than easy questions. Let's do a quick warm-up just to review the trick that I taught for this reaction. If I have a carbonyl and I react it with an alcohol, like, I think I did this last time, so let's go with something like this, with an acid catalyst. And the catalyst should really be at the top, so I'll move it around. But think about what kind of reaction this is and what we're going to do. But I'm more interested in the shortcut after you know the reaction, because the shortcut is what we're going to do for the next steps. This is an acetal or ketal under the category of acetal formation. And the shortcut, which I want you to pay attention to, we break the pi bond and we put a new bond to the carbon that used to, two new bonds to the carbon that used to hold carbonyl. We add the oxygens and the R groups. So let me show you what the product would look like. So we have this right here, no pi bond on it. What we do have is a new oxygen on each side. Whatever else is on it, 3 carbons, add that in. 1, 2, 3, 1, 2, 3. And there is my, in this case, it's a ketal. It's a very scary looking thing. It looks like a bug. Bells and whistles, that works perfectly as well. No worries. Okay, so now that we know what we're looking at, let's do a reverse, because your professors will ask you, show me the starting molecule that gave you this right here. Absolutely correct. Let's say I give you something that looks like, bear with me as I figure out how to draw this. Okay, there we go. I want to know the reverse. And so if I take my acetal or ketal and I place it into a solution of H2SO4, that will open it up. Oh, I just gave it away. Let me know in the comments if you knew that this was an acetal before I accidentally slipped that this was an acetal. And while you're working on that, if you're not yet subscribed, go ahead and hit the thumbs up and the subscribe button. I am hoping to reach 1 million subscribers, one live stream at a time, and I really, really can use your help. So go ahead, hit subscribe, tell your friends. Really, really appreciate it. The way that we know that this is an acetal is very simple. We find a carbon that has 2 oxygens on it, or rather, I see that the 2 oxygens seem to have a central carbon. And if that carbon has 2 oxygens, that right there is the acetal position. And the trick then is to identify that carbon and give it a carbonyl. Then you break the bond of the oxygens that's attached to it, and you give each oxygen a hydrogen to make it an alcohol. Now it looks like quite a mess. Let me see a scared emoji in the comments if you're thinking, oh my goodness, I hope I don't get this on my exam. But also, oh my goodness, I'm going to know how to do this in 2 seconds as soon as we're done here. So let me see those scared emojis followed by a happy face emoji to show me that you're excited for the trick, because all you do is this. This right here is my carbon chain. That's it. 1, 2, 3, 4, 5, 6, and 7. All I have to draw is 7 carbons. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, and 7. Let's move that over here. And what do I have on this molecule? Well, let's see. Carbon 1 has an alcohol, so let's add that on. Carbon 7 has an alcohol. Let's add that on. Carbon 4 has a carbon coming out of it that has a carbonyl. So let's try to track what I just said. Carbon 4 has this carbon coming out of it, and that has a carbonyl. There you go. That is the starting molecule that would have given me, or that did give me, this product. You are very, very welcome. All right. Please explain how it happened. So what happens is the alcohols will attack the carbonyl. And if this is confusing, let me know if you want me to show you another way to make it very, very obvious what actually happened here. Here's another way that you can think of it. If you redraw it exactly as you see it and just apply these cuts here, it'll be much more obvious. So that would be carbon 4, 3, 2, 1, alcohol. Attached to carbon 4 is this one. It has a carbonyl, so that's my aldehyde. And then I have 5, 6, 7, and 7 also has an alcohol. Now it's much easier to envision the alcohol attacks, and that is how I get my acetal. Should we try one more like it? All right, let's try one more like it, where I have a molecule that looks like, I'm trying to think of what I've seen professors use. As I draw this, would you have suspected that this is an acetal when you first saw it? Yes or no? We're reacting this with H2SO4. What do we get? Let's see. Identify the carbon that has the 2 oxygen bonds coming out of it. Turn that into a carbonyl. Break the bond between the oxygen and the carbon. Give it a hydrogen. Turn that into an alcohol. Let's redraw it exactly as we see it first so you can very obviously see what happened. Actually, I don't even have to do that. This is how obviously it came from that. All I have to do is break these bonds right there and pretty it up a little. So I have my carbonyl oxygen right there. Let's move the alcohols up just a little bit so they're not in each other's faces. That right there is an alcohol. That right there is an alcohol. And if I were to draw it out the way your professor is probably expecting to see it, 1, 2, 3, 4, 5, 6, 7, 8, 9. I have a 9 carbon chain. Room for that. And that is 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. What do I have? Carbon 5 is a carbonyl right there. Carbon 1 has an alcohol. 9 has an alcohol. And this right there, it's the same thing. It's just drawn in a different way. Please comment on the stability of the parent molecule. Will it be resonance stabilized? Resonance requires the ability to move electrons. And so none of these have anything extra to move around. Therefore, there will be no resonance. In general, an acetal is a pretty stable molecule. So the starting molecule here is quite stable. A diol is not, but the acetal itself is. All right, let's jump over to the next problem. Easy, medium, or hard? Let me know in the comments. Let's think. So we want to form I see medium. Well, this is not medium. This is easy, but we can do medium after. Or let me know if you agree. Easy, medium, or hard. We want to synthesize this molecule from any carbonyl, 2 carbons or less, plus any other reagents that we want to include. Looking at this, I'm knowing that it has to come from a carbonyl, 2 carbons or less. I can still apply the questions for synthesis of what is the same and what is different. And what I'm looking at here is I'm starting with 2 carbons and I'm ending with 3. So I have to find a way to grow the carbon chain, to add a carbon onto the chain. And the best way to do that, as I told you in the aldehyde ketone reaction section, part 1, which is linked in the comments below, Grignard is a great way to do chain elongation. Knowing that it's a Grignard, identify the carbon holding the oxygen. That right there was your carbonyl. Break that off. And that right there was your Grignard. And then we're good to go. Our starting molecule was an aldehyde reacting with a methyl Grignard, CH3MgBr. That's step 1. Step 2, H3O plus. And we get the product that we are shown here with an alcohol and that extra group added. Extra group, let me show in another color so you see where it came from, and this one also got added. With this in mind, let's see how we can take a molecule that looks like this. Let me know in the comments, easy, medium, or hard. and turn it into a molecule that looks like this. All right. What am I going to do? Where do I start? If you're not sure, put IDKY. I don't know yet, and I'll show you. So let's start with the basic questions. Question number 1, what is the same? And question number 2, what is different? What is the same is that I seem to have 4 carbons in my starting molecule and 4 carbons in my product. What is different is that I added a carbon onto the end of the molecule. But here's the problem. What reaction do I know that will keep an alcohol on a molecule and then add something to the other end of the molecule when there is zero reactivity, zero ability to add? There's nothing. In order to connect, I need a connector. I need a leaving group. I need a Grignard. I need some kind of attacker. And so we have to take a step back and ask ourselves, is that really what is happening? Or if the only area of this molecule that is reactive is the alcohol, then maybe this is where I have to add another carbon and then somehow figure out where to go from there. So if this is carbon 1, 2, 3, and 4, it would be here 1, 2, 3, and 4. And this is my new addition, carbon 5, which gives me a different way to think of it. So converting the parent molecule into a Grignard, then reacting it with formaldehyde to an alcohol is absolutely correct. I was thinking of the same thing in reverse. Oh, I see. I wonder if your reaction is actually faster. Let me show you what I was thinking, but this is a perfect situation of a scenario of there's more than one way to do this. Because what I was thinking is to grow the carbon chain first and then move the reactivity. To grow the carbon chain, I would have turned this into something that can be attacked by a Grignard, specifically an aldehyde. Attack it with a 1-carbon Grignard, which now gives me a 5-carbon chain, this being the new carbon that I added. When I add a Grignard, I add an alcohol, but then I was thinking of simply moving the reactivity, which we already saw how to do. This is going to be a little bit trickier. We're going to need an extra step here because we can't make a pi bond on the terminal end with an alcohol. It has to be a halogen. So I'll take a quick detour, turn it into a halogen. Then I can move the reactivity by turning it into a pi bond. And once it's a pi bond, I can turn that's a little bit of a Trump line. I can turn that into an alcohol. But this will be a second-degree alcohol. So yes, this is a couple of extra steps, but it completely works. So let me fill in the reagents, and then I'll go with what Imran had suggested, because I think that will be faster and fewer steps. So what I was thinking is PCC to the aldehyde, then that right there is adding a methyl Grignard. So CH3 MgBr, that's step 1. Step 2, H3O plus is just to protonate it. Then we want to turn that into a halogen, so PBr3. Once it's a halogen, I can eliminate. I'm going to the less substituted side, the non-Zaitsev product, the Hoffman product. So I'll use something big and bulky, potassium tert-butoxide in tert-butanol. As a reminder, these are previous reactions you've learned. So this is this chapter, this is this chapter, or this you may have learned in, I'll call this redox because it comes up in different chapters. The Grignard is what we're learning now. PBr3 is the alcohol chapter. Then this right here was the E2 chapter. Once we have the alkene, we're going to use an anti-Markovnikov alcohol addition. So we'll use BH3, THF, step 1, step 2, NaOH, H2O2. This is the alkene chapter, and that's our product. I want to try the other style because I hadn't considered that. Okay. So Imran, I'm sorry, I want to go back to your suggestion. First, we turn it into a Grignard. So this would be a similar set of reagents, but in a different order. So the first thing we're going to do is turn this into a Grignard, which means we need a halogen, something like bromine. We then, in a second step, turn that into this right here with an MgBr. Then, so we have the Grignard. Then we attack the formaldehyde, which is going to be a 1-carbon aldehyde, form telling us 1 carbon. This is a unique aldehyde, 2 hydrogens rather than 1. This will give me a longer, actually, no, that is right there. We're done. So fewer steps. Imran, this is a great, I wouldn't even have thought of this because my brain was immediately thinking add to the chain. You're turning the chain into something to add. This is perfect. So we're going to use same set of reagents. So we have PBr3 to get the bromine. Once we have the bromine, magnesium and ether, ET2O. Then the formaldehyde is step 1, step 2, H3O+. That is simply to protonate. And we have our product in 1, 2, 3 steps, where the one I gave you was 1, 2, 3, 4, 5 steps. Both correct, but if you can do 3 steps, I don't know, I think 3 is better than 5, so that is perfect. So look at this one for another moment. Look at this one, make sure you're comfortable with both. For converting an alkene to a primary alcohol, we can use hydroboration oxidation. Yes, and so that is, oh, whoops, did I jump too much? No, right here. So hydroboration is the anti-Markovnikov alcohol addition, which is what we used here. Hello, hello. You are very welcome. This tells me you're thinking. This tells me you understand the reactions. I love it. Let's end with something exciting. As I draw out the last problem, what I want you to let me know in the comments is which practice problem you found most helpful today in terms of not just the practice, but also hopefully a good shortcut that you walked away with so that you will have an easier time with this. And don't forget, for even more problems, put worksheet in the comments, and I will link you to my brand new practice worksheet where you can practice even more aldehyde and ketone reactions. Ooh, I should have made this harder. Okay, I'm not going to be that evil. Here we go. So this problem is one that professors love to ask. And they will say, show me all of the different starting molecules that you could have used to create this product. So show me the different combination. Let me make it bigger. The different combination of starting molecules you could have used to get this right here. But first, we have a question on the last one. So the third step added the extra carbon. I assume you're asking about here. So we had step 1 was oxidizing it to an aldehyde to make it susceptible to attack. Step 2 was the Grignard attack. So step 2 is where I added the Grignard to grow the chain. And then I did all the remaining, unless you're asking about this one. Here we had step 1. We turned the alcohol into a halogen so that step 2, we can turn it into a Grignard. And then step 3, instead of adding a Grignard to the carbon, I brought the carbon to my Grignard and I elongated the chain. So yes, that is what we're looking at here. Hopefully both make sense. All right, so final question. The combinations that we could have used to get this product with the Grignard is very simple. You find the carbon holding the oxygen, and you immediately recognize that that right there is where you had your carbonate. Now, in this chapter, we're only looking at ketones and aldehydes, and so I can systematically break off one piece and give you that as my Grignard. So if I break it here, then that right there was my Grignard. So all I do is I redraw everything as I see it. So option 1 is this molecule right here with the carbonyl. And the Grignard, I don't know where I'm going to squeeze it all in. I'll shrink it after I draw it. Option 1 is this one, plus the Grignard is this piece right here, which is that with an Mg, we put a Cl on it. So that is option 1, where I sliced in orange. Let's shrink it down so we have room. Option 2, we'll slice in a light blue, so that'll be here. Means my starting molecule is all of this, and that's my Grignard. So let's see how I get that. So this is, I'll just clean this up. Yeah, I'm going to have to redraw some here. Okay, so I have the carbon coming out of the ring is where I have the carbonyl. And then coming out of that, I have the isopropyl. I'll just change the angle a little bit. Then my Grignard is the other piece right there. Just a cyclohexane with an MgCl coming out of it. So this was option 2, where I sliced in blue. Let's shrink it down. And then let's show option 3, where we'll slice in light green right here. That means all of this was my starting molecule, and that would be my cyclohexane. I have to draw it differently so I have room. So I have my cyclohexane attached to the carbon that is the carbonyl, and I'm going to just turn the isopropyl to the other side like this, plus the Grignard, which in this case is this group right here. And that is simply a benzene ring with a Grignard coming out of it. We can call it MgCl. Let's bring this one up like that. And here are, oops, what on earth? I don't want to use a space tool. I want to use a drawing tool. There we go. Option 1, that was option 3, option 2, and option 1. These 3 different combinations of ketone and Grignard is how I got my product. Let me know if you got all 3, if you could only identify 2, or if you struggled with this. Question, we can use a ketone and treat with a Grignard reagent to convert it into a tertiary alcohol. Yes, exactly. And the question we had to figure out is, what was the ketone? What was the Grignard? And these are the 3 different options that would have all given us the same single final product. Would H3O mess up the Grignard reagent? Absolutely yes. So let me show you. If I tried a reaction where I had a CH3 MgBr, and I tried to attack a carbonyl, but I decided that I was cheap and I can only afford water because I have it in the tap. And so I dissolved my carbonyl in water somehow, if that even dissolves. Yeah, I guess so, right? Because that's kind of protic. Not protic, it's polar. The Grignard being so strong and so reactive is not going to go and work hard for that carbonyl. It's just going to grab a hydrogen off of water, acid, whatever I happen to have used. And what I get now is a CH3, which I had already. That extra hydrogen is grabbed from water. This right here is methane gas. This gas is going to bubble right out of the solution. I have a ketone that is wondering what the heck just happened. And then I have an OH minus from this thing that is a strong base, but this is way stronger, and that's why it got attacked. So great question. Let me know if that is clear. Please explain how to know what's a strong and weak base and nucleophile. Okay, so that's a topic that's a different topic. And so I'm not going to go into it now, but check out my, it's in the substitution elimination video series. It's one of the earliest videos on strong and weak nucleophiles, and I go through it in detail, the difference between a nucleophile, a base, a strong, and a weak. I think 2 cases better. Parent molecule has low steric. So if you're referring to this one, professors like to ask, show me all the combinations without necessarily asking about which one would react faster. But what you're saying is, if we had to rank them, we want to find a Grignard that is small, or meaning if the Grignard is small, it can have an easier time attacking, or if it's very bulky, it will not get attacked overall. And so in this case, it is very sterically hindered because even though this is small, it has to squeeze between 2 rings. In this case, we have a benzene ring and an isopropyl, and here we have a cyclohexane and an isopropyl. The benzene ring is flat. That means it has slightly less steric hindrance. This would be the easiest to access, then this one, and then this one. So yes, if your professor is asking for that next level, this is a very good thing to look at. Wow, yeah, you definitely know some advanced reactions. So most of the students I work with are in the undergraduate level in the US and some in Canada, UK, Australia, and so on. And at the undergraduate level, we just learn the basics, the straightforward reactions. So I'm not familiar with that. However, if you do have to know that, make sure that you actually go and learn that because you don't want to miss any questions on your exam. All right, that was a lot, but if you want even more practice, I've got you covered. Just comment worksheet and I will give you additional practice. The worksheet is not available on my website, but it's got well over a dozen practice questions on aldehydes and ketones. Comment live notes for a copy of today's session notes so you don't have to worry about scrambling to copy everything down. Now, tonight's session was just a tiny piece of the organic chemistry puzzle. And if you want even more sessions like this on everything, Orgo 1, Orgo 2, teaching sessions, practice, because today was practice, step-by-step video solutions for all the quizzes on my website, and bonus sessions when I do them, come join me in the Organic Chemistry Study Hall. The link is on the screen or leahforsci.com/join. You'll get access to my complete Organic Chemistry 1 and 2 video library with lecture and practice sessions. And you're not going to be going through this alone. You join my private Facebook group where you can post your daily study questions, get help with whatever you need when you need it. The link to sign up is leahforsci.com/join.